Hello, Stat 300. This is Professor Gonzalez, and I'm taking a look at homework from 5.2. And that 5.2 that we're looking at is coming from the adaptive side of ALEKS. And here we go. So I already did a little mini lecture on 5.2 on the assignment side of ALEKS. So if you want to take a look at that, but we're doing a lot of the same things. Let's get right into it. Question number 1 says a marble is selected from a bag containing 8 marbles numbered 1 through 8. The number on the marble selected will be recorded as the outcome. Consider the following events. Event A is the marble selected has an odd number on it. And select B, the marble selected has a number greater than 3. So remember, now what they're asking us to do here is they're not asking for probability on this one. They're just asking for the event. So basically, when they're asking for the event, they're just asking for what numbers fall into that event, the desired thing they're asking for, right? And if it was probability, you take that desired event divided by your total sample space. But that's not this isn't probability. This is just looking at the event of A or B. So I would like to do a little Venn diagram of this. And so if I say A, set A, and then we also have set B, the question is, are these mutually exclusive, or do they overlap at all? And I think they overlap, but let's see. Event A is the marble selected has an odd number on it, and event B, the marble selected, has a number that's greater than 3. So tell me what numbers are greater than 3. 4, 5, 6, 7, 8. You can see I was kind of tricky where I put the 5 and 7. Well, I put the 5 and 7 in that overlapping ring because A is what? A is the marble selected has an odd number on it, and the odd numbers would be 1, 3, 5, 7, right? So A is all odd numbers, and B is numbers greater than 3. So the thing to really notice, I think, here, well, first of all, event A is, I'm looking for the elements are in A or B. And A or B is just going to be 1, 3. Anyway, it's going to be these two, the 2 in the middle, and then the 3 on the right. But the problem is when you're using an OR statement, when you're using the formula, you might actually count. And this is here's the problem with the OR, is you might actually count A as being 1, right? Let's see. Let me start again. You might count A as being 1, 3, 5, 7, and you would not be wrong. And then you might count B as being 4, 5, 6, 7, 8. But where you would be wrong is the problem is you double counted this stuff right here, which means you counted it once in the green, calling it 5 and 7, and then you counted it twice in the orange, calling it, here's a 5 and 7 again. Whoops, you can't even see them. But anyhow, that's the part where you have to subtract out the and in the formula that we'll be seeing coming up real soon. Anyhow, event A or B is just the union of all those. It's just going to be, it's in A or B or both. So it's just going to be 1, 3, 4, 5, 6, 7, 8. Okay, don't double count them. And then event A and B, I'm looking for the elements that are in A and B, and that's just going to be the overlapping stuff right here. I think I used that, maybe. Anyways, the overlapping, this is called A and B. So A and B is just going to be 5 and 7. Now the last one here we're looking for is the complement of the event A. Now remember, the complement of event A means not A. So if I looked at, let me just write A up here. up top here. Remember, A would be the number, the selected numbers are odd. So A happens to be 1, 3, let's see. I don't even know if I really need to show all this. Yeah, I might as well now that I'm here. So the full sample space would be 1, 2, 3, 4, 5, 6, 7, 8, right? And what is A? I'll go ahead and do A in green. Once again, we see in our Venn diagram, A is 1, 3, 5, 7. A happens to be the odd numbers 1, 3, 5, and 7. So what's not A? So not A, I'm going to use brown, I think. Or no, that looks too close to orange. We're going to go with red. So not A is going to be the leftover, right? The opposite stuff. So that means the complement of A is just going to be the evens. 2, 4, 6, 8. Probably could have just said evens, huh? That did run through my mind. Anyways, the next question is question number 2. And it says, an ordinary fair die is a cube with the numbers 1 through 6 on the sides, represented by painted spots. Okay, thank you. I think we know what dice are. Imagine, wow, my computer is ramping up trying to upload this stuff to YouTube. Anyways, imagine, here I am right here. Imagine that such a die is rolled twice in succession and the face values of the 2 dice are added together. So we're going to have these 2 guys, we're going to roll 2 dice and we're going to add them together. Okay, you got to get that part down. We're rolling 2 dice and we're adding them together. The sum is recorded as an outcome of a single trial of a random experiment. Okay. So what we want to know here is the sum. So event A is the sum is greater than 9. So I think this is kind of hard to do unless you have something like this little guy. And I will go ahead and post some of these in the file so you have these little worksheets to help yourself. But if I want to find the sum is greater than 9, let's look at it. This chart shows all the sums. Maybe I should show the chart. Chart's like, so you roll a 1 and a 1 and the sum is 2, right? You roll a 3 and a 1 and so the sum is 4. So this just shows you all the different sums when you roll 2 dice, summing the 2 dice together. And remember what we're looking for. It says event A is the sum is greater than 9. Well, how many are there that are greater than 9? Well, greater than 9 is going to be the sum is 10, the sum of 11s are greater than 9, and the sum of 12 is greater than 9. So that gives us 1, 2, 3, 4, 5, 6. So if I want the probability that you get a sum that's greater than 9, that's going to be 6 out of 36, which is approximately 0.1 with a repeating 6, rounded to 2 decimal places. So we are going to write it as 0.17. Okay, and then the next problem that we're looking for is the sum is divisible by 3. The sum is divisible by 3. So the sum let's see. The sum is divisible by 3. So which numbers are divisible by 3? Well, 3 is divisible by 3, and 6 is divisible by 3, and 9 is divisible by 3, and 12 is divisible by 3. How many numbers will that be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 12 out of 36, which is approximately point repeating 3. And it says to round to 2 decimal places, so that's 0.33. And that's it. Okay, so you can see that little chart was handy. You could also look that stuff up on the internet. Basically, the sum of two dice chart, and you'll see a whole bunch of them. Number 3, it says in a packet of stickers there are 11 small stars, 8 big stars, 12 small rockets, and 10 big rockets. Kevin is going to choose one of these stickers from a packet at random to put on his art wall. This sounds like preschool or kindergarten or elementary school. What is the probability that the sticker Kevin chooses is big or a star? So this is, this is one of these situations where it's nice to pull out. Well, once again, our formula, right? It's nice to use our formula, and it's also kind of nice to be able to use a two-way chart to kind of see what's going on. So let's go ahead and do that. We have what? We have stars stickers, and we've got rocket stickers. Stars and rockets. And what else do we have? We've got big stickers, and we've got small stickers. So let's see. So tell us, yeah, here it is right here. It says there are 11 small star stickers. 11 small star stickers. Perfect. There are 8 big star stickers. There are 8 big star stickers. So how many star stickers do we have total? Looks like we got 19, right? Okay, let's continue to fill out 12 small rocket stickers. 12 small, whoops, that's big. 12 small rocket stickers, and then 10 big rocket stickers, 10 big rocket stickers, and 10 plus 12 is 22, and so this should all add up properly. Let's see. If we add up, okay, let's see, how many big stickers we have? We got 18. How many small stickers do we have? We've got, what's that, 23. And this should all add up to the same total right here. So we've got, let's do it this way first, vertically. 19 plus 22, that's going to give us, what's that, 41. And hopefully we get 41 going this way. 18 plus 23 also gives us 41, so that's all good. Okay, now that we have that going, and that wasn't totally essential, but when you're new at this, it might be kind of a good idea. But this is what we're looking for, really. We're looking for, chooses a big or a star. So we're looking for the probability of a big or star. Now remember, our formula says the probability of this, and I think I'm going to write this down below. The probability is going to be the probability of a big plus the probability of a star minus the probability of a big and, remember the overlap, and star. That's the stuff that we might have double counted. So what's the probability that you'll get a big sticker? And I think I'll use some color here. Probability of big sticker, that's going to be 18. Gosh, that was sloppy. It's going to be 18 out of a total of 41. And what's the probability that we get a small sticker? Well, small is going to be, oh, it's not small, it's star. That's probably where I need to be a little cleaner with that. It's star, so this is, let me just call this, make it clear, star instead of small. And that's star. Okay, what's the probability of a star sticker? Well, a star sticker, there are a total of 19 star stickers, so 19 out of 41. We're going to need to add these up, and the big question is, did we double count anything? And we could kind of double check by going through. Let's see, when we said we were looking for the probability of a big, that would have been this stuff, right? And then we were looking for the probability that it's a star sticker, that would have been this stuff. And oh yeah, we can see the intersection, we double counted, we counted 8 2 times. That's got to be taken out, 8 out of 41. Okay, and so then when you add this up and then subtract out 8, we're going to get, what are we going to get? 29 out of 41, which is approximately 0.707707317, and it goes on. And they want us to round to the nearest hundredth. So we could go ahead and round that to the nearest 10th hundredth. Look over here, oh, bigger than 5, so it's going to be 0.71 is our approximation. That's a probability we get a big or star sticker. Okay, let's move on to our last couple problems. What is this number? This is number 4. It's separated by my little thing I added there. This is number 4. Okay, number 4 says, a retail shop accepts only cash or checks. Suppose that 54% of its customers carry cash, 41% carry checks, and 75% carry cash or checks or both. What is the probability that a randomly chosen customer at the shop is carrying both cash and checks? Well, there it is right there. We're looking for cash and checks. Okay, so that's what is given to us here. What's given? Okay, so suppose I think I'll use color. What the heck? I always use color. Suppose that 54% of its customers carry cash. So that's saying the probability that someone's carrying cash, call it CA, I guess, is 0.54. And it also says 41% carry checks. Probability that someone carries checks is going to be 0.41. Let's see, suppose that 54% of its customers carry cash, 41 carries checks and, 41 carries checks, oh no, okay, I'm good. 41's carrying checks, man, it's hard to see here for me. And then finally, the last one is going to be, let's use another color. It says and, 75 carry cash or checks or both. Okay, so this one is going to be, this one's just going to be the probability of cash. There's the keyword or, cash or checks, and that's 0.75. Okay, so this one's a little bit tricky. So we kind of need to use our formula here. I'm going to try to color coordinate this. Remember the formula that says if you have the probability of an event and then the word or another event, that's simply going to be, I'm just trying to color coordinate this so we can see it, that's simply going to be a probability of the first thing, which was the probability of cash, plus the probability of the second thing, which is probability of checks. And then we have to subtract out the overlap, if there is any, which is the and, probability of cash, and, whoops, I don't want that to be that color. It looks way too close to purple, isn't it? So probability of cash and, remember the overlap that we have to cancel out or subtract out? So what do we have? Well, what we have is we definitely have this purple stuff right here, right? We definitely have the probability of cash or checks was given is 0.75. And we definitely have this red stuff right here, which is the probability of cash, which happened, which happened to be 0.54. And then we have plus and a minus, and we definitely have our green probability of checks, which is 0.41. And then we have to subtract out our gold, which we don't have, was not given to us. which is the probability of cash and checks. Now the key thing that's tricky here is, look at, that's what they asked for. What's the probability that a randomly chosen customer at the shop is carrying both cash and checks? And they didn't give us cash and checks, but they did give us everything else in the formula. So this guy right here is the variable, just like if you're solving for x in algebra. So let's go ahead and take care of this. First thing you're going to do is combine like terms, right? And when you add those together, you get 0.95. So now we've got 0.75 equals 0.95 minus probability of cash and checks. So we go ahead and subtract this from both sides, right? 0.95, because we're trying to isolate. We're trying to isolate our probability of cash and checks. And when we subtract that from both sides, we get a negative 0.2. Now, we don't want to know what negative probability is, so we just essentially multiply both sides of the equation. You don't even really have to show this as much anymore. You negate both sides. You multiply both sides by -1. And when you do that, that just changes the sign on both. And the beauty of that is now we get exactly what we want. We want to know what's the probability that you have cash and checks. And there it is. We're able to do this by using our formula, which is the general addition rule of OR that happen to have an AND in it. And then we solve for AND, and there's the answer. Let's do our last problem, which is number 5. It says a company has both male and female employees. The company has shirts and jackets with the company logo to give away to employees. For each of the company's 226 employees, a manager asked which piece of clothing the employee prefers. The preferences are based on gender and summarized in the table below. Okay, so something that I usually like to do with these problems is add them up and just make sure our tables are good. I'm sure they didn't mess the tables up, but if we take 97 plus 37, we get 134. And if we take 77 plus 15, we get 92. And let me zoom in here. And if we add 134 plus 92, we get 226, which perfectly matches with there's 226 employees. And we can do it the other way as well, right? We can say 97 plus 77 is 174. And we can say 37 plus 15 is 52. And when we take 174 plus 52, we get 226. Okay, so I need a little glass of water. Okay, so let's do it here. Suppose an employee of the company is chosen at random. Answer each part. Do not round intermediate computations. That basically means don't round in the middle of your work. Only round at the very end when they say round to the nearest hundredth. And when you don't round in the middle of your work, just try to take values that's in your calculator, right? Don't round like to the hundredth in the middle of your work, because that can really throw off your answers, especially when you're putting them into a computer program and they're supposed to have some leniency, but you know, if you round early, it really can screw up your results. So don't round in the middle of your work, only round at the end, the final answer. What is the probability that the employee is female? Let's do A right here. Probability that the employee is female. And it looks like to me we've got 92 females. So that is going to be 92 out of the total, which was 226. And we throw that in the calculator, and that gives us approximately 0.40707. They said, please round to what? Nearest hundredth. We go over 1. We go 2 places, which is the hundredths. and it is a 7. So this is going to be approximately, rounded to the nearest hundredth, 0.41. And this is the probability that you're going to randomly select a female, or the probability that you're going to select a female. Once again, suppose that an employee of the company is chosen at random. What's the probability to get a female? And we've got it at about approximately 41%. Let's do part B. Oh, here it is right here. And then part B, what's the probability that the employee is female or prefers a shirt? We know probability female or prefers a shirt. Well, we know that from the formula, this is the general addition rule. And it's going to be the probability that it's a female plus probability that the person prefers a shirt minus the probability of a female and prefers a shirt. Once again, the stuff that you're double counting needs to be justified or subtracted out. So let's first start off the probability that the person is a female. And let's do that. Let's not use our decimals right now. Let's just go ahead and use fractions. Okay, so probability is a female. We already did that, and we used green, I believe. So here it is right here. There are 92 females. So it's going to be 92 out of the total of 226, plus the probability that a person prefers a shirt. We'll go ahead and do that in red. And where's the people that, oh, you know what? I needed to do this so you can see if there is overlap happening, because I'm a teacher and I like to try to teach things. So anyways, probability of a shirt, well, the people that have shirts are these people right here. Okay. How many people had shirts? Well, that's the event. So that's 174 out of the total sample space or total people, 226. Now, was there any overlap? Did we double count? Yeah, we did. That's definitely overlapping green and Christmas red all together. So there's 77 that we accidentally double counted. So 77 out of 226 must be subtracted out. You do the math, you add, you subtract. You end up getting 189 over 226, which is approximately 0.83629. And we're going to round that to the nearest hundredth. So tenths, hundredths, that is 5 or bigger. Yes, it is. So 0.84. 0.84, there we go. And so that is the answer to the probability that we get a female or the person prefers a shirt. And that's it. Okay, well, I hope that helped out, and I hope you're having a great day, and you guys take care. We'll talk to you shortly on the next time around. Bye.